Good to go.
Well, I hope this will be as memorable as the other two talks. I've attempted to do something pretty nice here. So, I'm a person who likes to go to used bookstores and buy math books. And I have a lot of them. I have, well, close to 10,000 of them. And these are a couple of pictures from my home. It's turned into a library. And I take it pretty seriously. Over a period of about 30 years, I've accumulated a huge amount of notes on algorithmic art. And you can see that they're really distilled down quite a bit of interesting information. For example, this is actually taking fractals that create severed Riemann surfaces, and I unpeel them so that I can look at underneath the Riemann surface and expand out fractals in ways that haven't been seen before. And sometimes I just leave them as is. And what you see are branch cuts. And what I did in the previous slide was I figured out a way of lifting up the flap so you can see underneath and see what's going on. And this is a talk I gave at Laser about 10 years ago. I was an artist in residence at Jurassic, and this is the kind of stuff that I was doing. This is algorithmic art using color theory and Boolean algebra and fuzzy logic and finite element analysis, all sorts of things. I get results. I have trademarks. I won awards on publications and other things. So this result that you're going to see tonight goes back a long ways, like everyone else. And I used the Star Trek allusion because I'm saying there are a lot of things that I could show you. This is one of many things. So if you haven't noticed, I'm wearing an Escher t-shirt. I love MC Escher. And actually, this is on my t-shirt. Escher was a graphic artist, although I think he was really a fine artist in every sense of the word. He did tiling of the plane in Euclidean geometry. That's the geometry we all know about. He also did some stuff in spherical and elliptical geometry, so he was looking at anamorphic art reflected on a sphere. And he also did hyperbolic tessellation, so that if this were projected upward onto a curved surface, it would look completely normal, but this is distorted so that essentially the curvature is reflected. So, again, three geometries. These are the ones we know about. Euclidean, that's the stuff we studied in elementary school. Spherical geometry is this kind of stuff that navigators use for ships and for planes. And most people haven't seen hyperbolic geometry. It deals with large astronomical objects in space that literally dent space-time. And it describes the curvature of the space-time. In fact, Einstein prevailed on Minkowski and Riemann in the area of hyperbolic geometry. All these geometries are defined relative to a conic. In one case, in Euclidean, it's a limiting case of a parabola. Spherical geometry is related to a circle or an ellipse, and hyperbolic geometry is related to a hyperbola. And if those of us who have had analytic geometry remember conic sections of the following kind. If you compute the various quantities, you can then look them up, and it'll tell you exactly what kind of conic you've got your hands on. There's some cases that are degenerate, and there are cases where you've got like circles with imaginary radii, which are imaginary. There are also imaginary versions of the other conics. So there are three different kinds of geometry: elliptic, parabolic, and hyperbolic, otherwise known as Euclidean. And you can measure angles, and you can measure lengths. This is a lovely table that Yagelon put together, which distills all of the different rules, the identities with trigonometry in one table. So I was thinking, Escher died in 1972. He died before the era of personal computers. So these are the kind of questions that Escher might have asked if you would have gone further into mathematics, if you would have had a computer. What happens when you have a conic section where the coefficients are complex? They're not real. They have both a real and imaginary components. How would we use an imaginary conic as a reference for being able to create a new kind of geometry? Was it possible? What happens if we allow for complex curvature? And we'll see in a minute what I mean by that. If the curvature has both non-real and real and imaginary components that are non-zero. So Escher used physical means. He used physical devices, wood blocks, ink, and etc. to be able to do what he was doing. But let's say that we work with stuff in the complex domain. Let's start fresh and approach it from a totally general approach. And to do this, there are 4 math models that you could use. Somerville, which was the original paper written in 1913, where he actually shows equations for elliptic and hyperbolic geometries in terms of this curvature parameter. Positive will get you elliptic geometry. Negative will get you hyperbolic geometry. 0 is flat. Woods in 22 pretty much did somewhat the same thing, but he defined non-Euclidean geometry related to that matrix that I showed you a couple of slides back, which describes the conic section. Question is, does it really have to be symmetric? Hint, it doesn't. Wiley, in 1970, approached it using projective geometry. So he made use of the matrix and used it to be able to compute distance and take the matrix and compute its adjoint, which is a complex conjugate, for angles. That's the basis of projective geometry. And Polya did something very strange, which I'll show you in a little bit. So the 1913 book has the equation. You can notice that K appears in the equation, and so the coordinate transforms and all of that are shown. And what I asked the question is, if K is complex, if K is real, you got elliptic geometry. If K is negative, you get hyperbolic geometry. But what happens if K is complex? Everything hangs together. The same rules, equations, and all that should be 0 are 0. If I draw lines and I figure out what the intersection point is, and ask the question, is the point on the line? Yes, it is. And so I go through and I do all the check. Nothing breaks, which is astonishing. It tells me that there's yet another form of geometry that's sitting there waiting, that's been undiscovered for over 100 years. Woods from 1922, this is his formulation. And it turns out that if you set things up so that you're dealing with an imaginary conic, these 2 models involving the hyperbolic functions and the circular functions produce exactly the same answers. Everything collapses together into one. And a little bit more introduction to projective geometry is the Wiley book. Very similar looking stuff to the stuff that you saw in Woods. And there's a lot of equations for that. But if you look at the elliptic lengths and the orientations and the angles, you'll notice they correspond perfectly between elliptic and hyperbolic models. Basically, the 2 models converge. Now, this is the thing I was telling you about Polya. He uses this particular equation, and he uses the imaginary component of this equation to compute the area of the polygon. It's a signed area indicating whether it's counterclockwise or clockwise. He never does anything with the real component. And it turns out the real component also takes you into this new kind of geometry that involves complex distances and angles. So what does this look like? What would this kind of geometry produce? This. So I use a random number seed to create 5 points that define a conic section. In this case, it's an imaginary ellipse. I compute the distance of every point from the origin, and I get both a real component and an imaginary component. And you'll notice that the elliptic distance and the hyperbolic distance are identical, just like I told you that the two models converge. Similarly, the elliptic angle, hyperbolic angle, they also converge. And you can see that basically it's redundant information, but it's absolutely gorgeous. These depict literally the complex plane being twisted and wrung dry, almost like a dish rag. And as I said, the models converge, the models agree. So with that in mind, I just look at one of these things. Again, an imaginary ellipse looks slightly different than before. And here's an imaginary hyperbola. They're all looking very unique in the way that they appear and the distortions that are imposed on the plane. So why care about it? Well, it bridges all these different geometries. Right now, as what we know, we have 3 discrete geometries: Euclidean, elliptic, and hyperbolic, and they're all separate. And there are separate equations for all of them. Well, this work actually says that all 3 of those geometries are edge cases. They're special cases of a meta-geometry, a supergeometry which is larger and more robust than the ones that we are familiar with. We can do exact computations on a machine, the kind of thing that Escher wishes he would have had. You can visualize this to do all kinds of interesting work in graphics and relativity theory, mapping, charting geodesy. New way of looking at that interpretation. So when Polya throws away half of the data, that data actually has some value in relation to this new geometry. Why does this matter? It matters because we can understand geometry through algebra, and it unlocks new ways of being able to model the world. And these are the conclusions. Geometry is not just one of 3 geometries. There's a whole continuum of potential geometries that are out there. And you'll see in a moment what I mean by that. This also says that those 3 trigonometries that you saw earlier, there's a trigonometry which is more the general case that subsumes both the models for hyperbolic and for circular. And we're talking 2 dimensions here. This can be generalized upward to 3 and 4 and 5 dimensions. Quadratic surfaces are in 3 dimensions. This shows that space can twist in ways we haven't looked at. Geometry is not a dead subject, it's dynamic. And performing complex mathematics actually does things to the complex plane in very interesting ways. We can simulate what is going on with this, and in a sense, Escher now has the ability to do a laptop. And this is something I think the other 2 presenters would agree with, that mathematics usually becomes relevant when it's describing the nature of the universe. And there's a paper, it's a delightful paper that was written by Eugene Wigner in 1960 that says that mathematics is unreasonably effective in being able to describe natural phenomena. So this is where we were before. Those of us who studied elementary school geometry, that's Euclidean, that's the flat plane. If your k squared happens to fall on the y-axis, you're in hyperbolic space, or you're in inverse hyperbolic space. You've done a Möbius transformation. If you're on the real axis, you're in elliptic space, or you're in inverse elliptic space. Does anyone here speak Latin?
A little bit.
Yeah.
It means, you know what that means? It means,
Zero
here be
lions.
lions. This is uncharted area up to this point. We only know about this because it's hyperbolic geometry. We only know about this because it's elliptic geometry. We know about the default case, which is Euclidean, the world we know about from school. This is an entirely different set of geometries. There's a whole continuum of geometries out there, of which what we know currently is just a special case of that. So I started doing this, I started by wanting to be an artist. And to be an artist, I wanted to know exactly how to go beyond what's currently been done. So I took the equations that existed that were underlying the ideas of Escher, and I said, okay, what happens if I completely generalize everything? And so what will break? And it turns out nothing broke. So I spent a long time trying to understand what all that means in terms of interpretation, physical interpretation. So trying to be an artist, I had to study more mathematics than you would ever study in graduate school. So then that's my little couplet that I say. That basically, art and science are two sides of the same coin, if you will. And number one, you have every reason to question what I'm saying. I have code literally on this machine that I can run for you. You can specify whatever parameters you'd like, and I can generate images on the fly. We don't have the time for it. If you want code, ask me. I will send you the code. You will be able to do with it what you will. I have a copyright license on it, and you can do with it what you will. And these are what the references I've used. If you wanted to know about conic sections, this is a great place to go. Polia has the complex variable model. This is Jagiellon's 3x3 table. This is the Wiley book that I used to create the visualizations. Struick, if you don't like projective geometry, by diving in by reading Coxeter, this is a general introduction. Introductory geometry. Manning has actually recapitulated a lot of the stuff that's in Somerville. Zwicker, if you ever want to understand why spirographs look the way they do, that relates to complex numbers and circles. This is the Somerville model that I showed you that holds together. And this is Shenstone Woods' book, which has a lot of that stuff in higher dimensional geometry, like 3, 4, and 5 dimensions. And that's what I